We are now going to move on to analyzing algorithms that involve 3 for loops. These are fundamentally exactly the same as the algorithms that we've done before. It's just that now we're going to have 2 summations that are going to be more than simple to analyze. So we might need to be a little bit careful in how we analyze those. So let's just try to jump right into this. We're going to let t of n be the runtime. And then we write it as a triple summation, just like we've seen before. The thing inside takes constant time. So this is the sum from I equals 1 to n of the sum from j equals 1 to I of the sum from k equals 1 to j of c, because again, the inside takes constant time. Just as we did with double for loops, we're going to start with the innermost summation. So we're going to start with the k summation. Notice k, the summation index, does not appear inside of the summation. Therefore, for all intents and purposes, c is a constant. So we write t of n is equal to the sum from I equals 1 to n of the sum from j equals 1 to I, doing nothing with those. And then that innermost summation, we're taking the summand and multiplying by the number of terms. The number of terms being the top bound minus the bottom bound plus 1 times c. We can simplify that to c times j, so let's do that very quickly. So we're going to write that as cj. And now comes the part that is noticeably different in the fact that we still have 2 summations and one of those summations variables appearing inside of the summation. So what are we going to do? Again, we need to start with the innermost summation. That summation has to do with j, that is the summation index. So what we're going to do is need to deal with that either by bounding or by using formulas. Notice this is an arithmetic sum. We're summing up j. So let's use the formula because we haven't done that in a little while. So t of n is equal to the sum from I equals 1 to n of, you could factor the c out and then use exactly the arithmetic sum formula. So this is c times the formula for an arithmetic sum. Let's write off to the side so we can see what's happening. The formula is 1 to n of I is n times n plus 1 divided by 2. So we're going to use that exact formula. However, our top bound is I, so we're doing I times I plus 1 divided by 2. The only difference between these formulas being the c, which I can factor out, and the fact that j is playing the place of I, and I is playing the place of n. So now, let's do some arithmetic on this. We can combine some constants and distribute and things like that, and write this as t of n is equal to the sum from I equals 1 to n of c over 2. And then if I distribute this I get I squared plus I, which we actually have formulas for both I squared and I, so why not try to use those? Let's factor out the c over 2 and write this as c over 2 times the sum from I equals 1 to n of I squared, and then we're going to distribute the summation, so I'm going to add a bracket here to symbolize that. We also have a sum from 1 to n of I. And just as we did with the j summation, let's write off to the side the formula we might need, just so we can have it there for you. We have the sum from I equals 1 to n of I squared. This is the one that's a little weird looking. This is n times n plus 1 times 2n plus 1, all divided by 6. So we're going to use that formula and the one that we used before to write down our final answer here. This is t of n is equal to c over 2 times that first one we're using the I squared formula, so let's use our purple. We have n times n plus 1 times 2n plus 1, all divided by 6, coming from our second formula there, plus the second summation, we're going to use the I formula, which was n times n plus 1 divided by 2. And as a whole, we now have a closed form expression, meaning there are no more summations. This involves what we call basic operations, addition, multiplication, division. And that is a closed form expression. Therefore, we can just identify the complexity of this expression. The first term here is going to be in n times n times n cubed, and the second one is going to be n times n, which is n squared. So, t of n, the running time, is in theta of n cubed. And this is a Similar example to what we've seen before, the one thing to be careful of with triple summations versus double summations is, does the summation index appear inside of the summation? If so, you're going to need to use formulas or bound. And this, you need to keep track of what is the summation index. It's not always going to be I, it's going to be potentially J, as we saw here, or in the second case it was I again. It could be theoretically any letter inside of there, so make sure you're checking what is the summation index and does that appear inside of the summation.